We want to create computer agents that are able to process natural languages for two main reasons. The first one is to communicate with humans, the second one to obtain information from written language. We examine the problem from the point of view of a specific information-seeking task. These are text classification, information retrieval, and information extraction. Programming languages have defined language models, for example, a set of strings in Python. Programs can't be enumerated, so they're specified by a set of rules called grammar. It is more fruitful to define a natural language model as a probability distribution over sentences rather than a definitive set, since natural language are ambiguous. A written text is composed of characters, so the simplest language model is a probability distribution over sequences of characters. A sequence of written symbols of length n is called an n-gram. Therefore, we can have unigrams, bigrams, trigrams, etc. They are especially useful for language identification, spelling correction, or gender classification. The major complication of an n-gram model is that the training corpus provides only an estimate of true probability distribution. The process of adjusting the probability of low-frequency count is called smoothing. Laplace said that if a random Boolean variable x has been false in all n observations so far, then the probability of x to be true is 1 divided by n plus 2. With so many possible n-gram models, how do we know what model do we choose? The answer is through cross-validation. The evaluation can be a task-specific metric, such as measuring accuracy on language identification. Alternatively, we can have a task-independent model of language quality, where the higher the probability, the better. Returning to model over words than characters, all the same mechanisms applies equally to word and character models. The main difference is that the vocabulary is larger. Word n-gram models need to deal with out-of-vocabulary words. To get a feeling for what models can do, we build different n-grams that you can see in the picture. Text classification is also known as categorization, and it consists as, given a text of some kind, deciding which predefined set of classes it belongs to. Language identification and gender classification are examples of text classification. Another example is spam detection, where words such as for cheap or you can buy are symbols of spam. Another way to think about classification is as a problem in data compression. A lossless completion algorithm takes a sequence of symbols, detects repeated patterns in it, and writes a description of the sequence that is more compact than the original. In effect, compression algorithms are creating a language model. To do classification by compression, we first lump together all the spam training messages and compress them as a unit. Given a new message to classify, we append it to the spam messages and compress the result. We also append it to the ham and compress that. Whichever class compresses better adds, this is, the fewer number of additional bytes for the new message is the predicted class. The idea is that a spam message will tend to share dictionary entries with other spam messages, and thus will compress better.
The information retrieval is a task based on finding documents that are relevant to a user's need for information. This task is built into information retrieval system, IR, such as the search engines. An IR can be characterized by a corpus of documents, a set of queries posed in a query language, a set of results, and the presentation of said results. The first IR systems work on a Boolean keyword model. In this model, each word in a document collection is treated as a Boolean value, that is true if the word is inside the document. This model was simple to explain and implement, but it had some disadvantages, such as the degree of relevance being a single bit. This meant that there is no guidance on how to order the relevant documents retrieved. These days, most IR systems have abandoned the Boolean model and use models based on the statistics of word counts. A scoring function takes a document and a query as inputs and returns a numeric score that represents how relevant a document is. The higher that value is, the most relevant it is considered. An example of an IR scoring function is the BM25 from the CAPI project. Now we know what an IR system is, but how do we know if it is performing well? Traditionally, the performance has been calculated using two measures, precision and recall. The precision measures the proportion of documents in the result that are relevant, and the recall measures the proportion of all the relevant documents in the collection that have been included in the result. Some IR algorithms examples are the PageRank algorithm and the HITS algorithm. PageRank was invented to solve the problem of the relevance scores, which, for example, could make the official web page for IBM appear after other pages that could mention IBM a lot of times. The HITS algorithm works as a query-dependent algorithm. This means it must be computed each time for each query. In some information retrieval queries, there may be a question. This introduces us to question answering, which is a different task in which the answer is not a ranked list of documents, but rather a short response. It could be a sentence or even just a phrase. Ask MSR is a good example of a typical web-based question answering system. Information extraction is the process of acquiring knowledge by skimming a text and looking for occurrences of objects and relationships between them. A typical task is to extract instances of addresses from web pages. In a limited domain, this can be done with high accuracy, but when the domain gets more general, more complex techniques and language models are required. The simplest type of information extraction system is the attribute-based one. This system assumes that the entire text refers to a single object and obtains attributes from it. It also obtains clues about an attribute from its context. An example about a more advanced type is the relational extraction systems. In general, these systems work well for a restricted domain with predetermined subjects. When the information extraction must be attended from noisy or too varied input, we need a better approach than the ones we have seen so far. The solution is to use a probabilistic model rather than a rule-based model. The simplest one is the hidden Markov model, or HMM. HMMs can be trained from data and therefore they can keep up to date as text changes over time. An example of this training could be how the HMMs learn from a structure of dates and applies probabilities to it. HMMs have two big advantages. They are probabilistic and therefore they are tolerant to noise, and they also have a graceful degradation with missing characters and words that gives us a probability indicating the degree of match, not just a Boolean result indicating whether it was a match or a fail. As a brief summary, the points that we have treated in this topic are probabilistic language models based on Ngram, the evaluation of said models, text classification and compression, information retrieval systems and algorithms, question answering, and information extraction systems and techniques.